Section 7.1 Example 5, on page 510, we have exponential functions are often discrete. In problem 4, interest is paid only once a year, so the graph consists of individual points corresponding to t equals 1, 2, 3, and so on. It is not continuous. Both the table and the graph show that there is never exactly $1,500 in the account, and that the account will not contain more than $1,500 until the 9th year. To model a discrete situation using an exponential function of the form y equals a times b to the x power, you need to find the growth or decay factor b. If you know y values for two consecutive x values, you can find the rate of change, r, and then find b using r equals y2 minus y1 divided by y1, and b equals 1 plus r. So we saw that at 9 years we would have over $1,500, and at 8 years it was below $1,500, but because you only get the interest once a year, there is no line drawn through these points, so we don't have exactly $1,500 at any point. Example 5 says the table shows the world population of the Iberian lynx in 2003 and 2004. If this trend continues and the population is decreasing exponentially, how many Iberian lynx will there be in 2014? So the world population is 150 in 2003 and 120 in 2004. Recall that y equals a times b to the x power is the equation for exponential growth or decay. Since we're looking at exponentially decreasing, we have exponential decay. And we are going to rewrite this as a times 1 plus r to the x power, where 1 plus r is b, and we can use these two values right here to figure out the rate of decay. Let x be the number of years since 2003, and let y be the population of the Iberian lynx. On the previous slide, we had that r can be found by using y2 minus y1 over y1. In this case, y2 is 120, y1 is 150, and we put 150 on the bottom as well. This becomes negative 30 over 150, or negative 0.2. The previous slide also told us that we can find b by using 1 plus r. As we can see in the equation above, we substituted 1 plus r for b. We just found that r is negative 0.2, so we can plug in 1 plus negative 0.2, which is just 1 minus 0.2, and this gives us that b is 0.8. Since 2003 is our starting year, you can note that the years from 2003, if it is still 2003, would be 0, and the population was 150. That means we can use 150 as our initial amount. However, if you were not given your initial amount within your data, you could solve for your initial amount A by plugging in the x and y values. Since we have a y value of 150 and an x value of 0, we get 150 equals A times our B, 0.8 raised to the 0 power. Anything to the 0 power other than 0 gives us 1. So we have a times 1, therefore we know a is 150. Now to figure out how many Iberian lynx there are in 2014, we need to figure out how many years have passed from 2003 to 2014. So if we subtract 2014 minus 2003, we get 11 years. So that becomes our x, or the number of years since 2003. This gives us the equation y equals 150 times 0.8 to the 11th power. This leaves us with the answer: if the 2003 to 2004 trend continues, there will be approximately 13 Iberian lynx in the wild in 2014. The work for this problem is written out on the next few slides. And now I would like you to try number 7, write an exponential function to model each situation, find each amount after the specified time. A population of 120,000 grows 1.2% per year for 15 years.